Greetings, everyone. Here's the start of Chapter 6, Section 6.1, and the title of this section is Area Between Two Curves. And so what we're doing in this section here is really applying the skills of the idea of the concept of integrals. And so we're going to be using the tools that we gained in Chapter 5 and trying to apply them to some physical situations like the area between two curves, and then in the next section finding volumes. So this is what it's about, and like I said in class, this is not overly complicated, so we should be able to get a good understanding just from the video lecture here. So let's suppose we have these two curves. I know one's a straight line, the one on top, and the other one's a curve, but curves are generic. Lines are generic curves, so they work just fine for us here. And so we have two curves, here, f of x and g of x, and I know you can probably see in the picture that this is from -1 to 3, but we're just going to call it from A to B. And what we want to do is be able to represent the area bounded between these two curves. And much like we did in section 5.1, where we're just trying to find the area bounded by the curve in the x-axis from A to B, we're going to set this up in the same way. And so some of this stuff is going to look awfully familiar. We would start by first figuring out the width of our rectangles, the width of our subintervals. And so we would still take b minus a divided by n. And of course we'd get x sub 0 would be equal to a, and then x sub 1 would be a plus delta x, and then x sub 2 would be equal to a plus 2 delta x, and then the next one dot dot dot, getting down to the nth one, would be a plus n times delta x, which of course equals b. And so we start off by setting up our subintervals in the exact same way. Next, what we do is, like before, we need to figure out the height of our rectangles and whatnot. So let me just draw a rectangle right over here, like this. Some typical rectangle. Now, as usual with the rectangle, we calculate its area as base times height, and the base is going to be delta x. I'm going to write it on top just because it fits a little better on the screen. But what I have to do now is figure out what the length or the height is of this rectangle. I need to figure out what this is right here. And so just like before, we can take any value in this subinterval here, and we'll call it x sub I star. And from that x sub I star, we want to be able to calculate the height. Well, if I want to figure out this part of the height right here, I would just plug in x sub I star into the function f, and that would give me the height for that one. And if I wanted to figure out the height on this interval over here, I'd just plug in x sub I star into g. And then from there, I can actually take those and figure out what the entire length is going to be. But remember, as we talked about a rule earlier, whenever we want to find distance from between 2 points that are vertically oriented in the xy plane, it's top minus bottom. So all I really need to do is figure out what the difference is, f of x sub I star minus g of x sub I star. And so that length, the height of the rectangle, is going to be just the difference of the outputs of the function at this x sub I star. Alright, so with that in mind, let's go figure out what the area of the rectangle is. So the area of one of these rectangles is equal to base times height, and so let's say we're going to have f of x sub I star minus g of x sub I star, and that's the height, and the base is going to be delta x. So as we did before, we set up our subintervals, figure out our delta x, set up the subintervals, we figure out how to represent the height of one of the rectangles so that we can represent the area of one of the rectangles, and we calculate the area. Now, of course, we're going to need to add all these areas together. The actual area is approximately equal to the sum from I equals 1 to n of adding all these areas of these rectangles together. So it's just going to be f of x sub I star minus g of x sub I star delta x. And so there is an approximation to the actual area. Now, you should recall, how do we make that approximation better? We choose more rectangles. How do we make the approximation exact? We take the limit. So the actual area is the limit as the number of rectangles grows without bound, goes to infinity, of the sum from I equals 1 to n of this f of x sub I star minus g of x sub I star delta x. And that's the actual area between those two curves. But let's wait a second for a moment. We're back to that section 5.1 complicated notation. I just want to note that this is on the interval from A to B. In 5.2, we learned a shorthand notation for this limit. You may recall, I hope, that the shorthand notation for this limit was just an integral. And so we can translate this to being the definite integral from A to B, the endpoints of the interval in which we're generating this area. And then what does our integrand look like? Well, we have to take this expression here and make that our integrand without x sub I star this time. We're going to choose just x like we did before. So this is going to be f of x minus g of x. And then delta x, remember, becomes the dx. It's that relic that reminds us the variable we're integrating with respect to, and also the independent variable of the expressions that we're dealing with. So, well, there it is. All we're doing is taking the definite integral of the difference of the two functions, where f is the one that is the top function, meaning, I don't want this thing, pick up a pen, there you go. The top function, meaning the one it's above, g of x, which is just the bottom function, the one that's below f, okay? So all we have to integrate on the interval is the top minus bottom. And then we can generate the area bounded by the curve, between the two curves, I should say. Note, because we're always choosing top minus bottom, no matter where the shaded region is located in the xy plane, when we're finding the area bounded between two curves, we should always get a positive number. Okay? Always get a positive number because we're taking a greater and subtracting a lesser, which is going to be positive. So these answers will always come out to be positive. Example number 1. Find the area bounded between y equals 1/2 x squared minus 3 and y equals 2x plus 3 on the interval -1, 3. Pause the video, go sketch a picture. This is just a parabola and a line, and take a look at what's going on. Alright, so hopefully you have a picture now, so you can see what's going on. This is the graph. It's the same graph we drew the rectangles on earlier. And so we can very quickly see that the linear piece is on top and the parabolic piece is on the bottom. And so, top minus bottom, we can set up an integral as the definite integral from -1 to 3 of, again, the linear function is on top. So it's going to be this 2x plus 3 minus 1/2 x squared minus 3 dx. And that's actually fairly straightforward to evaluate. So let's go through a few steps. And so, let's see, we have a -1/2 x squared. When I distribute the minus sign over here, we'll have a plus 2x. And it looks like a plus 6 when we combine the 3 and the opposite of -3 dx. And now here we can just run through finding an antiderivative using the fundamental theorem. And so when I take the antiderivative of x squared, I get 1/3 x cubed, and then I have to multiply that by negative 1/2, so I'll get negative 1/6 x cubed. I don't know if I'm going to be able to squeeze this on the screen. Plus x squared, the antiderivative of 2x, plus 6x. And then we need to evaluate that at negative 1 and 3. So if we evaluate that at 3, we're going to get, looks like negative 27/6. I'm going to put this up here. Plus 9 plus 18. Okay, and then I got to subtract from that. What happens when I plug in 1? When I plug in 1, I get negative 1/6 plus 1 plus 6. So negative 1/6 plus 1 plus 6. And so let me see here. If I distribute the minus sign, I get a positive 1/6 and a negative 27/6, which makes negative 26/6. And then we get 27 minus 7, which is 20. And then this is minus 13/3 plus 60/3. And so 50, 47. So it looks like we have 47/3 as our answer here for this. You should double check my arithmetic, make sure I didn't make any mistakes. But that's our answer. So again, the key thing here is when we set up the integral that we subtract the top function minus the bottom function. So you have to look at the graph and make sure that you recognize which one is on top and which one is on the bottom. Use your appropriate limits of integration and then use the fundamental theorem. Now in all the examples that follow, I'm just going to give you the two functions and then you're going to go sketch a picture and figure out what the area is. So in this next example, the two functions that we're finding the area between are y equals root x and y equals negative x, and we're looking on the interval from 1 to 4. So go ahead and pause, draw the picture, set up the integral. Let's just set up the integral. We don't actually have to use the fundamental theorem right now because the examples that we're going to be doing here are fairly straightforward. If you want to practice, go ahead and practice setting up the fundamental theorem. Or evaluating these definite integrals with the fundamental theorem, but I'm just going to set up the integrals and assume that you can perform the rest. So hopefully you were able to get the appropriate picture and the appropriate definite integral. Here is the picture, and so it may be hard to tell because on this interval here, this is the square root graph, y equals the square root of x. But it looks almost linear, and of course we know this is y equals negative x. And so the rectangles that we draw, and you should get into a habit of drawing the rectangles just to make sure how things are going. We'll have delta x here. I'll show you an example of why I'm saying that after a while. But we have delta x here, top minus bottom, and we'll have a root x minus negative x. So the area that we're finding is the definite integral. It's found by using the definite integral from 1 to 4. Of the square root of x minus negative x dx. And of course we can simplify that algebraically, by just taking the opposite of negative x. But I'm just trying to set it up so you guys can see exactly how it is. Top minus bottom from 1 to 4. Next, find the area bounded between the curves y equals 2 minus x squared and y equals x. So go pause the video, sketch a picture, and see what's going on. Now you may be saying, Mr. Francis, but you didn't tell us what the interval is. That's correct, I did not. Now go look at the graph. Pause it, go look at the graph. Hopefully you can now see what's going on. The region here that we're talking about is closed off. Okay, there is a region completely contained within the boundaries of these two curves. Let's take a look. So, if we take a look at the picture of this thing, you could see that we have a region completely enclosed above by the parabola and below by the line. If we draw a little representative slice like this, we get our delta x. top is the parabola, bottom is the linear piece, top minus bottom. And so the area that we're going to find here is the definite integral. Hey, we need our limits of integration. How are we going to get those? Well, this is where your algebra skills come back to play. But we can still set up the integrand part and put the definite integral portion in later. Let's go back to the picture here for a moment. I need to figure out the point of intersections of the graph here and here. So we have 2 minus x squared. And that has to equal x. And so using our algebra skills, we're going to solve this system, or rather this equation here. And so we're going to get 0 is equal to x squared plus x minus 2. We'll do a little factoring. And so we get x plus 2, x minus 2, minus 1, excuse me. And our two solutions are going to be x equals negative 2 and x equals positive 1. And so we now know our definite integral is from negative 2 to 1. And there we go. Now we just need to work out the answer using the evaluation theorem or the fundamental theorem of calculus. So if no interval is given, then go look at the graph and figure out if there's a region that's completely bounded by the two curves, and you're going to be finding the area of that region. All right, example 4. Find the area bounded between the two curves, x squared minus 4x plus 3, and y equals negative x squared plus 2x plus 3. Pause the video, go sketch. Use a calculator if you need to, or a computer to get the sketch going for now. And then take a look at what's going on, set up your integral. Alright, so the graph looks like this. And so it should be fairly obvious that the parabola with the leading coefficient that's negative is going to be on top. And just by looking at the picture, and because it's concave downward, and the parabola with a positive leading coefficient, the x squared being positive, is going to be on the bottom. So when we take a look at our representative slice like this, and our delta x, top minus bottom is fairly straightforward. We still need to figure out the points of intersection on the x-axis to figure out where we're integrating from. So we'll have our x squared plus minus 4x plus 3 equal to negative x squared plus 2x plus 3. And the 3's, the 3's cancel, so we don't need to worry about those. If I bring the 2x, the negative x squared over to the left, we get 2x squared over here. Bring in the 2x over to the negative 4x, we get negative 6x equals 0. We can factor out a 2x, and then we get x minus 3 over here. And so we get x equals 0 and 3 as our solutions. And so we'll take our area to be the definite integral from 0 to 3 top, which is, as we said, the negative parabola here, the one that's opening downward, minus the bottom, the one that's opening upward. Don't forget your dx. I know a lot of you probably are. Also, notice that I keep using parentheses. I don't really need parentheses around the first expression, but I do need them around the second expression, so I remember to distribute the minus sign, because we are subtracting here. So make sure that you use enough parentheses to get this done properly. Hopefully you got that answer. Example 5. Find the area bounded between the two curves, 3x cubed minus x squared minus 10x. And y is equal to negative x squared plus 2x. So take out a calculator. You need to take a look at this region here, because this one is going to be a little different. So go take a look and figure out what's going on. No, really, you should go take a look, because some of you I know are just waiting for me to show it, but you need to practice on your calculators. You need to make sure that you know how to do this stuff without my help. So try it first, find out what's going on, go write your integral, and figure out an answer before you take a look at mine. Alright, now let me show you what the graph looks like here. This graph here has two different regions, because the curves intersect not twice, but 3 times. And so we need to set up actually 2 different integrals to work this one out. Now, why do we need two different integrals? Well, if I were to draw a rectangle on the left region over here, of course this is delta x, top minus bottom, this top piece right here is going to be the cubic, and the bottom piece is the parabola, and so, or the quadratic. And so, top minus bottom is the cubic minus the quadratic. If I move over to this region over here and draw a rectangle, as you need to practice doing, top minus bottom is now the parabola, or the quadratic, minus the cubic. And so the order of the subtraction has changed for the different subintervals, and so we need to figure out, we need to write two different definite integrals to represent this area bounded between these two curves. And so let's go ahead and, we need to figure out where these two curves intersect, and so let me go back over here. So I got 3x cubed minus x squared minus 10x equals negative x squared plus 2x. So we've got some algebra to do here. Let's bring everything over to the left-hand side. If I add x squared to both sides, looks like both x squareds cancel, and so that's nice. If I add 2x to both sides, or subtract 2x from both sides, I get a negative 12x. Excuse me for pausing there for a second. And then I can factor out a 3x here, and we get x squared minus 4. And so I think, without having to write another step and squeeze it someplace else, you could probably see that our three solutions are 0, negative 2, and positive 2. And so, going back to the picture, we can clearly see the 0 right there. Over here is where the x value is negative 2, and over here is where the x value is positive 2. And so we know how to set this one up. From negative 2 to 0, I want the cubic over the quadratic. And then from 0 to 2, I want the quadratic minus the cubic. Alright, so the area here, the first definite integral, as we said, from negative 2 to 0, is going to be the cubic on top. Let me double check that. Let's see, 3x cubed minus x squared minus 10x. That's the top function. Minus negative x squared plus 2x. That's the bottom function. Dx plus the definite integral from 0 to 2, and then we reverse the order of the subtraction. Negative x squared plus 2x minus 3x cubed minus x squared minus 10x. And of course, dx. So there you go. Now let's take a look at another graph. This is going to be a slightly different situation here. And so when you see this, what's going on here, we're gonna want to try this with a slightly different technique. So take a look at this picture. We have the curves y equals x minus 1 and x equals 3 minus y squared. So we have a sleeping parabola here. And there are a couple different ways of approaching this problem, and one is going to be easier than the other. And if we do this with rectangles in our usual orientation, hopefully you can see that if I draw a rectangle over here with delta x, and then a rectangle over here, and here's delta x, that we have two different bounding functions. On the first one, on the rectangle on the left, we have the linear piece on top, and we have the lower part of the sleeping parabola on the bottom. But on the rectangle on the right, we have the upper part of the sleeping parabola on top, and over here we have the lower part of the sleeping parabola on the bottom. So we would really have to do this using two different, and I would miss the point completely, using two different integrals if we're going to do this using delta x, or with respect to x. Because I have the functions that are bounding the rectangle change on different intervals. But there is a way to do this with a single integral, and I'll show you that in just a sec. So suppose instead of drawing the rectangles where they have a smaller width, smaller horizontal length than vertical length, suppose I decide to draw them with a different orientation, and I draw them this way, like this. I always have on the right-hand side, no matter where I decide to draw the rectangle, if I draw it down here, if I draw it way down here, or whatever, the right side of the rectangle always is coming from the sleeping parabola. The left side is always coming from the linear piece. And so I can use a single integral if I always have the same boundaries on the left and the right, or the top and the bottom. However, there's a slight difference in how we do this, because if I slice the rectangles horizontally like this instead of vertically like we've done every other time, this little length over here is no longer delta x, this is delta y, because this length is vertical, so that's a slice along the y-axis. So what does this mean? Well, all it means is we need to rewrite both functions, if they're not already so, as functions x in terms of y, meaning solve for x. And then instead of thinking this as the integral top minus bottom, this is going to be the integral right minus left from values along the y-axis instead of values along the x-axis. So we have, y is equal to x minus 1, and we have x is equal to 3 minus y squared. Now, the second equation here is the sleeping parabola is already solved for x, so I don't have anything to do there. The first equation, though, is easily solved for x as just y plus 1. Now, again, I said a moment ago, I could figure out the horizontal length as right minus left. And so my integral that I write for the area here, and I'll leave the limits off for just a moment, is going to be the right function, which was the sleeping parabola, so 3 minus y squared, minus the left boundary, y plus 1, and then we're going to integrate with respect to y, dy, because we have those delta y's in the picture. Now, what are my limits of integration? Well, here we have to figure out the y values of the points of intersection of these curves, because we're integrating along the y-axis. We have a delta y. So we need to figure out the y-coordinate for each of those, and so we're going to set these two expressions equal to each other. So 3 minus y squared equal to y plus 1, and I'm just solving for the y values here. So 0 is equal to y squared plus y minus 2, just bringing everything over to the right. Factoring, we get a y plus 2 times y minus 1. And so we know that we're going to get a negative 2 and a positive 1, and so we'll integrate from negative 2 to positive 1. And there's how we're going to calculate the area. Now, I know some of you may be freaking out right now thinking, oh my God, what did he just do? But I really didn't do much different than what we did before. All we did is we changed our perspective. We re-rotated, instead of using rectangles that slice up and down vertically with a little delta x, we sliced it horizontally. And so we have a little delta y. That little short region is parallel to the y-axis. And so I just solve my equations that were given for x so that I have x in terms of y. And then it's just the integral of right minus left, how we find distance in the horizontal distance in the xy plane, right minus left. Let's try another example. I gotta figure out, excuse the flipping around there, I forgot to pause the recording while I try to figure out what example number we were actually on. So I didn't call the last example any number, so I'm just numbering the next, this one here is example 6. Find the area bounded by the curves y equals x minus 2 and x equals y squared. Go take a look. You may have trouble graphing x equals y squared on your calculator, but you should remember how to do that. Just in case you may have forgotten, if we solve this for y, we'll get y is equal to plus or minus the square root of x. So you have to plug it in two different functions into your calculator, positive root x and negative root x, to get the sleeping parabola that comes from this. All right, go see if you can figure it out on your own. All right, so if we take a look at the picture here, again, if I were to try to do this with respect to x, meaning I use rectangles that are sliced in this direction here, I have to take top minus